Okay, so let's continue our discussion of norm spaces and Banach spaces. So last time I introduced the space of bounded linear operators from one norm space from another, and we saw that when the target is a Banach space, then this space of bounded linear operators is also a Banach space. So now we'll look at another example of a way to obtain a norm space from a given norm space. So I'll be talking about subspaces and quotients. All right. So let me just recall briefly what a subspace is. You should remember this from linear algebra. V will always be at least a vector space, usually a norm space. So we say a subset, and I've been using this notation. It doesn't mean a strict subset. I'm just kind of used to using this notation from 18100A, and the textbook used this notation for just being a subset, not necessarily a strict subset. So quick note about that. So a subset of V is a subspace if for all two elements in the field of scalars and elements in W, their linear combination is also in W. Okay, so W is closed under taking linear combinations. And so it's quite easy to prove, and I'll leave this to you, that the subspace of a normed space, of a Banach space, is itself a Banach space, meaning it's complete with respect to the norm it inherits from V. It's a Banach space if and only if it's a closed subset of V with respect to this metric we have induced by the norm. Okay? I mean, you can, let me talk our way through it real quick. Assuming W is a Banach space, we want to show W is also a closed subset of V. So that means you need to show, for example, that one equivalent way of showing this is that every sequence of elements from W that converges to an element of W. Okay? Now, take a sequence in W that converges to some element in V. We now want to show that elements in W. Then that sequence converges in W, or is Cauchy in W. And since W is a Banach space, there must be an element in W which it converges to, and therefore, by uniqueness of limits, that limit of that original sequence must lie in W. Okay? And now go in the opposite direction, assuming the subspace is closed. You want to show that now this subspace is a Banach space, meaning it's complete. Well, let's take a Cauchy sequence in W. This is also a Cauchy sequence in V. Therefore, it has a limit. This limit has to be in W since W is closed. And therefore, every Cauchy sequence in W has a limit in W. And therefore, W is a Banach space. Okay, so I didn't write out the details, but we talked our way through it. So let me, since we're taking a trip down memory lane, I just recalled what a subspace is. Now, given a subspace, we can obtain another vector space with the data of the space and the subspace called the quotient. So let me recall the quotient. So this is about briefly recalling what the quotient is. So let's take a subspace of V. We define an equivalence relation on V by saying that V is related to V prime if and only if V minus V prime is in W. Okay? Now, what do I mean by equivalence relation? V is always related to V because the difference of V is equal to 0, which is an element of W, because W is a subspace and therefore a vector space in its own right. If V is related to V prime, then this implies V prime is related to V, simply because V, again, if this is in W, then its minus is also in W. And so this is reflexivity. And then we also have transitivity, that if V is related to V prime and V prime is related to V double prime, then V is related to V double prime. Okay? Just simply take V minus V double prime and add and subtract V prime. Then you obtain the sum of two elements in W, which must be in W. So this is an equivalence relation. And so then we define the equivalence class of V. This is the set of all V prime in V, such that V prime is related to V. And then we define a new set, V mod W, to be the set of all equivalence classes. Okay? And instead of writing the equivalence class of V, we typically write V plus W instead of the equivalence class of V. Okay? So you think of the equivalence class of V as being V plus kind of all elements of W. Okay? Or two elements are the same if they differ by an element of W. Okay? So this is a set, but it becomes a vector space with the addition and scalar multiplication operations defined in a kind of natural way, with V1 and scalar multiplication is just the equivalence class given by lambda times V. Okay? Now, you have to take a second and make sure that these operations are well defined, which I'm sure you did in linear algebra. What do I mean by well defined? Well, these are two equivalence classes, so if I take two other representatives, say v1 prime and v2 prime, do I get the same equivalence class as I did with the unprime, meaning does v1 prime plus v2 prime plus w the same equivalence class as v1 plus v2 plus w, and this is not too hard to say, or to see. Okay? All right. So v mod w, which is typically how you pronounce this v slash w, v mod w is a vector space, and so note we can identify w, so just the set w with the equivalence class 0 plus w, which is also equal to w plus little w plus capital W. Okay? Okay. So, when we first started talking about norms, I also introduced what was called a seminorm. Now, a seminorm, recall, satisfied not all three properties a norm satisfied. It satisfies homogeneity, meaning how scalars pull out, and also the triangle inequality. But it didn't satisfy positive definiteness, meaning the seminorm could be 0 for certain non-zero vectors. Okay? You know, how could that arise? How could a seminorm arise? Well, think of taking the maximum of the derivative of a function, right, as being a norm, or as being a potential norm. Then it satisfies homogeneity and the triangle inequality, but it is not a norm because the derivative of constant functions is 0, but constant functions aren't identically 0 if you think of them as elements of, say, the space of continuously differentiable functions. Okay? But this next theorem says that if you mod out by the elements in a vector space on which the seminorm is 0, then you get essentially a norm space where the norm is given by this seminorm. So if you mod out by the elements with 0 seminorm, you get an actual norm space. The statement is let's take a seminorm on a vector space V. Then we define E to be the set of all V in capital V, such that this seminorm of these vectors is 0. This is a subspace of V. And if I define the following function on V mod E, so what is it? This is simply the norm of the representative V of this equivalence class. So if I define a function like this, so then this function defines a norm on the space V mod E. Okay, so in short, if I have a seminorm and I mod out by all the elements with seminorm equal to 0, then I get an actual normed space where this norm is, essentially the seminorm. Okay? Okay, so let's prove this. So why is this a subspace? Well, if I take two elements in this space of elements that have zero seminorm and two scalars, and if I take the seminorm of its the linear combination formed, I want to show this is equal to 0, and this follows essentially by homogeneity in the triangle inequality. This is less than or equal to, if I apply the triangle inequality and then pull the scalars out, this is less than or equal to plus. And if these both have seminorm equal to 0, this is equal to 0. And now, remember, a seminorm is always non-negative. So if I show something is less than or equal to 0, it's also, then it must be equal to 0. Okay? So first off, we define this function. So now let's show that this defines a norm on V mod E. We need to first show it's well defined because, I'm defining it in terms of, a representative of this equivalence class. All right? So this. And what does this mean? I.e., if if I have two equivalence classes with, or if I have the same equivalence class with two different representatives, V and V prime, then, and I should write E, not W, then the norm of V equals the norm of V prime. Okay, and therefore this function is well defined. Now, how do we do that? Again, it's going to be essentially the triangle inequality. So, suppose V plus E equals V prime plus E, meaning I have two representatives for the same equivalence class. And that means there exists a little e, capital E, such that V is equal to V prime plus E. Then, if I take the norm of V, this is equal to norm of V prime plus E. And by the triangle inequality, this is less than or equal to norm of V prime plus norm of seminorm of E. And now since E is coming from this set of all vectors with seminorm equal to 0, this is equal to 0, and therefore I get the seminorm of V prime. So I've shown that the seminorm of V is less than or equal to the seminorm of V prime. Now there was nothing, this argument is symmetric in V and V prime, all right? If V is equal to V prime plus E for some element in capital E, so is V prime. So I can also switch I can also switch V and V prime, meaning I've shown that V is less than or equal to V prime, and the norm of V prime is less than or equal to V, and therefore their two norms agree. So this function here is well defined. And so I'm going to leave it to you now to check that this function now, which is well defined on V mod E, does in fact satisfy all the properties of a seminorm. I mean, it's non-negative, so from essentially, you know, the homogeneity and triangle inequality property of the seminorm, the triangle inequality and homogeneity of this function then follow. And, you know, we've essentially equated all elements with seminorm equal to 0 to 0. So this is why it's also positive definite. So I'm going to leave that to you. Okay? Okay. Now there's one other way, if we're given, so in this process we started with a seminorm on a space, identified the subspace of all, you know, if you'd like, 0 norm elements, and obtained a new norm space. But you could start off with a norm space, a closed subspace of that norm space, and obtain a new norm space on V mod W, if W is that closed space. You know, in sort of similar fashion, where I define this norm this way, and well, the norm on that space won't be the same as this one, but that'll be in the exercises. Okay? Okay. So that's about, you know, this is kind of concluding the elementary section of functional analysis, meaning the bare bones of Banach spaces and norm spaces. And now with the rest of this lecture and then next lecture, we're going to get into, you know, kind of the fundamental results of functional analysis related to Banach spaces. So these theorems that I'll now be stating and proving in the coming couple of lectures have names attached to them, so you should definitely know what they are, what they state, what they don't state. But to prove them, I first need a result from metric spaces, which I did teach last semester, but we didn't cover this theorem. I can't remember if I covered it when I taught 18100B. I don't think I did, but so this is about when can you write, or in what way. Okay, so let me just state the theorem and then I'll interpret it for you. So this is Baire's theorem. It also goes by the name of the Baire Category Theorem, although it has nothing to do with, you know, category theory as is, you know, I guess used today. I don't know if category theory gets used or if it just is created for itself. But you know, Baire's category theorem is the only category theorem that I know. So what does it state? If M, so this is, again, this is a theorem about metric spaces, so not, you know, necessarily norm spaces. So if M is a complete metric space, and Cn is a collection of closed subsets, of M such that M is their union. So this is so I have an N here, so specify this is n is a natural number, then at least one Cn contains an open ball, Bxr, which I'll recall this is set of all y and m such that the distance from x to y is less than r. So at least one Cn contains an open ball. Could be stated more succinctly as at least one Cn has an interior point. Okay? So sometimes in applications these Cn's are not necessarily closed, but if M is equal to the union of these sets, then it's also equal to the union of their closures. And so what this theorem says is that if you can write a metric space as a union of sets, then the closure of one of those sets has to contain an open ball. And this, now, let's think a little bit of what it means for, or there's a specific terminology for when the closure of a set does not contain an open ball. That means it's nowhere dense, or that's the phrase we usually use for that is that it's nowhere dense. So Baire's theorem says that if you have M equal to the union of a collection of sets, then the closure of one of those sets has to be dense somewhere. Okay? Or you can't write M, a complete metric space, as the union of nowhere dense subsets. Okay? All right. And so this theorem is quite simple to state. It's quite very useful and, quite powerful in applications. In fact, you can use this theorem to give an alternative proof to something that hopefully you saw in your analysis class, which is that there exists a continuous function which is nowhere differentiable. Maybe I'll put that in the exercises. Maybe I'll just point you to it somewhere. We'll see. All right, so the proof is by contradiction. I believe this is the first contradiction proof that we've done in the class. So in 18100A and B, you start off, everything is by contradiction. Let's suppose not, i.e., you can find there is a collection of closed subsets of M such that M is equal to this union. And what we're going to do is we're going to find a point that's not in this union and therefore not in M, and that'll be our contradiction. We'll use the completeness of M to obtain this point, because how we're going to obtain this point is as a limit of a certain sequence, and to be able to say that this limit exists, we're going to show this sequence as Cauchy. All right, so we're going to build up this sequence inductively, and I will write this inductive proof kind of carefully this first time, and then in the future I'm just going to say, okay, choose P1 this way, choose P2 this way, continuing in this manner, we obtain a sequence of points this blah, blah, blah. But at this stage, I'll write this inductive proof kind of carefully. Okay, so suppose not. Since M certainly contains an open ball, and C1 cannot contain an open ball, this implies M does not equal to the first closed set. Otherwise, the first closed set would contain an open ball. Thus, there exists an element P1 and M take away C1. Now, C1 is closed. This implies that its complement is open. And therefore, I can find small epsilon 1 such that the ball centered at P1 of radius epsilon 1 intersects C1 equals the empty set. Okay? Now I'm going to pick C2. Now, the ball centered at P1 of radius epsilon 1 over 3, this is not contained in C2 because, again, this is by contradiction. So we're assuming that M is written as a union of closed sets, and none of these closed sets contain an open ball. So this open ball cannot be contained in C2. Okay? And therefore, there exists some point P2 in this open ball centered at P1 of radius epsilon 1 over 3 such that P2 is not in C2. Now, again, C2 closed implies that there exists an epsilon 2 less than epsilon over 3, so we can make it very small if we wish, such that the ball centered at P2 of radius epsilon 2 intersects C2 equals the empty set. Okay? So now I've picked P2, P1 and P2. Now, at this point, I would usually say, continuing in this manner, we obtain a sequence of points, but let me write out the argument carefully. Suppose there exists k points P1, Pk, and positive epsilon 1, epsilon k, such that two things occur. So epsilon k is less than epsilon k minus 1 over 3, and which is less than epsilon k minus 2 over 3, and so on, all the way down to epsilon 1 over 3 k minus 1. So if you like, k here is bigger than or equal to 2. And Pj satisfy. Pj is in the ball centered at Pj minus 1 of radius epsilon j minus 1 over 3. And the ball centered at Pj epsilon j intersects Cj equals the empty set. Okay? So let me star those two properties right there. We're going to obtain another point satisfying those two properties. Okay? And I don't know why I'm being a stickler. It doesn't really matter, but let me put a 2. Because that's not necessarily satisfied for P1, but okay. Now I want to show I can obtain a k plus first point satisfying those two properties. Okay? Again, this is just formally saying that once I've chosen P2, then I can choose a P3 doing this argument again, and it'll satisfy everything P2 satisfied with epsilon 1, except now with epsilon 2. But now I'm just making it more formal. So now again, M is the union of all these closed sets, none of which contain an open ball. So since the ball of radius pk epsilon k over 3 is not contained in C k plus 1, there exists an element pk plus 1 not in ck plus 1. Or I should say, over 3 such that pk plus 1 is not in ck plus 1. Okay? So let me, there's pk epsilon k over 3. ck plus 1. So maybe they're not disjoint, maybe there's some overlap, but then I can find a point pk plus 1 in there that's not in ck plus 1. So then there exists an epsilon k plus 1, which I can choose very small, say smaller than epsilon k over 3, such that, again, because ck plus 1 is closed, pk plus 1 is not in ck plus 1, so I can find a small ball around pk plus 1, disjoint from ck plus 1. Ball intersects ck equals the empty set. Okay. Okay, so then given k points, I can then choose a k plus first point satisfying these two bullet points here. All right? So by induction, we have found a sequence of points pk in M such that, and epsilon k, so if you like, k starts at 2, epsilon k and 0, epsilon 1, such that for all k, those two bullet points hold, such that which I denoted, which I put a little star by, star holds. So I'm talking about these 2 points. So when I say star, I mean these 2 statements here. Okay? Okay. Now, now let's show that this sequence is Cauchy. So now I claim how do we do that? this follows. So I'm not going to write out the full epsilon m argument, but I'm just going to write down the crucial estimate that proves this. This follows from the fact that for all k, for all L, if I look at the distance between pk and pk plus L, because, you know, in the end, when I look at, if I want to show something's Cauchy, I need to take the difference of two, or the distance between 2 points. One, you know, I can choose as the point occurring earlier in the sequence, and then one occurring later. Anyways, then by the triangle inequality repeated, I can write that this is less than or equal to the distance from pk plus 1 plus the distance from pk plus 1, pk plus L. And now I could do the triangle inequality again, and so I get that this is less than or equal to the distance from pk to pk plus 1 plus the distance from pk plus 1 to pk plus 2, and so on until I get to the distance between pk plus L minus 1 and pk plus L. Okay? Now, by star, what's in yellow, okay? pk plus 1 is in the epsilon k over 3 ball centered at pk. So this is less than epsilon k over 3. And the same thing here, less than epsilon k plus 1 over 3 plus epsilon k plus L minus 1 over 3. And now all of those are less than, if you go to the first one, is less than epsilon 1 over 3k minus 1. So then this is less than epsilon 1 over 3k plus epsilon 1 over 3k plus L. Yeah. Okay? And now I can actually sum this up, right? This is equal to, and this is strictly less than epsilon 1. And if I summed now from L equals k to infinity, 1 over 3k, this is equal to 1 over epsilon 1, 3k, 1 over 1 minus 1/3, which equals epsilon 1 over 2, 3 to the minus k plus 1. Okay? So the distance between a point pk and pk plus L is less than some constant times 3 to the minus k plus 1. So if k is very large, this is very small, independent of L. Okay, so I shouldn't have used L here. And that's m. Okay? So this shows that the sequence is Cauchy. So since M is complete, there exists P in M such that these elements pk converge to P. And now we're going to show this point P does not lie in any of the CJs. And we'll do it by showing it's essentially in all of these balls, Pj epsilon j. Okay? All right, and it's kind of a similar computation to what we just did. So now for all k natural number, if we look at the distance between pk plus 1, pk plus 1 plus L, again, if I just go back to this computation right here, right? This we proved was less than epsilon k plus 1 times 1 over 3 k plus 1 plus, or actually 1 over 3 plus 1 over 3 squared plus 1 over 3k plus 1, no, k plus L. Or I'm sorry, I think that's just L. And now, this thing is less than if I replace it by the infinite sum. So this is less than epsilon k plus 1 times the infinite sum again, m equals 0 to infinity, 3 to the minus m, which equals what? So this is again equal to epsilon k plus 1 times 3/2. Okay. Now, okay, so we've proven that the distance between pk plus 1 plus L is less than epsilon k plus 1 times 3 over 2. Let me take the limit as L goes to infinity. Pk plus 1 plus L converges to the point P, so I get that the distance between pk plus 1 and the point P is less than or equal to 3/2 epsilon k plus 1. And remember, epsilon k plus 1 is less than 1/3 epsilon k, so this is less than 1/2 epsilon k. All right? And since pk plus 1, remember, this is in the ball of radius 1/3 epsilon k. So I get that the distance between pk and P is less than or equal to the distance between pk and pk plus 1 plus 1 and P. We get this is less than or equal to 1/3 epsilon k plus 1/2 epsilon k, and this is less than epsilon k, which means that P is in the ball of radius pk of radius epsilon k, which by the second property up in star, the fact that all these balls are disjoint from, each of the balls is disjoint from ck, means P is not in ck. Now k was arbitrary here, so we conclude that P is not in this union, which is equal to m, and that's a contradiction. Okay? Okay. So, I mean, you know, I said the strategy at the top of the proof, you know, the technical argument maybe muddled what was going on, but again, the point is, you know, you can build, if this conclusion does not hold, you can build a sequence which has this disjointness property from this collection of open sets such that the sequence is Cauchy. And because M is a complete metric space, you can then extract a limit P. This limit P will have all the properties that these PKs had, namely that they're not in any of the CKs. And therefore, this point P does not lie in the metric space, which is nonsense. So we arrived at our contradiction, and therefore, Baire's category theorem is proven. Okay, so that's Baire Category Theorem. Let's now use this to prove some fundamental results of functional analysis. So the first result we'll prove is what's called the Uniform Boundedness Theorem, which says that if you have a sequence of bounded linear operators on a Banach space, then pointwise boundedness implies sort of uniform boundedness, okay? Or boundedness in a uniform boundedness in the operator norm. So let B be the Banach space. And let Tn be a sequence of bounded linear operators, which we denoted last time by this script B, to some other norm space V. Okay, so I didn't write that, but V is a norm space. If for all B in capital B, sup n of Tnb norm is less than infinity. So if I assume that this sequence is pointwise bounded, then I can conclude that they're uniformly bounded, namely the sup of the operator norms are bounded. Okay? All right. So we're going to use the Baire Category Theorem. So we're going to write the Banach space B as a union of closed subsets. What will be these closed subsets? Remember, we're trying to find kind of a uniform bound on the Tn. So kind of just playing around. So let's define the subset of B to be Ck. This is a set of all elements B and B, such that the norm of B is less than or equal to 1, and sup n Tn of B is less than or equal to K. All right? All right. So first off, these are closed. So I should say, what is K? K here is a natural number. Ck is closed. Why is this? Well, we need to show that a sequence converging, a sequence of elements from Ck that converges to an element of Ck. So if Bn, this is a sequence of elements in Ck, and Bn converges to B, then the norm of B is equal to the limit as n goes to infinity of the norm of Bn. And each of these is less than or equal to 1, so the limit has to be less than or equal to 1. Okay? And so I shouldn't, maybe I'll use I have the Tn's, I have the Bn, so let me use m. And for all m a natural number, Tm applied to B and norm, this is equal to the limit as n goes to infinity of Tm Bn in norm, because these are bounded linear operators and therefore continuous. Okay, so Tm of b is equal to the limit as n goes to infinity of Tm of bn. Okay? And now the norm of Tm of bn is always, well, this is always less than or equal to k, because the bn's are in ck, and sup of all these guys is less than or equal to k, so that's also less than or equal to k. All right? Thus, b is in ck, which implies ck is closed. Okay. Now, the closed ball, or I shouldn't say it's not the closure of the open ball, but the closed ball, b in capital B, such that b is less than or equal to 1, this is equal to the union over all k of ck. Why? So first off, each of these is contained in this closed ball, but I'm assuming by star that no matter what b is in the Banach space, sup over n of these is less than infinity. So there's always some integer k given a b, so given a certain b in this set, I can always find a large enough integer such that this is less than that integer. So it has to, every element in here has to lie in one of these sets c sub k. So this is equal to the union. So this is a complete metric space because it's a closed subset of M. So this is a complete metric space written as the union of a union of closed subsets. So by Baire's theorem, there exists one of these sets containing an open ball. Of the form B naught delta naught. So one of these CKs contains an open ball. Now we're going to use this K and to derive a uniform bound. So if E is in B, and let's see. So let's write it this way. If B is in the open ball of radius delta 0, centered at 0, so this means, i.e., the norm of B is less than delta 0, then B naught plus B is in this open ball centered at B naught, and therefore sup n of Tn of B naught plus B norm is less than or equal to K. All right? So this ball is contained in Ck, and therefore, if I take the sup over n of T sub n applied to this thing, this is less than or equal to K. All right? But then I conclude that sup over n of Tn applied to B, which is less than or equal to sup n. So I'm going to add and subtract B0. Okay? So let me actually write this as sup of Tn B0 plus Tn B0 plus B. This is less than or equal to by the triangle inequality, and then carrying the sup through, this is less than or equal to sup n Tn b0 plus sup n Tn b0 plus b. And so b0 is certainly in this ball, which is contained in ck. So this is less than or equal to k. And this is still in that ball of radius delta 0 centered at b0. So it lies in ck. And therefore, this sup is also less than or equal to k equals 2k. So I've shown that if I take any element in the open ball of radius delta 0, then the sup over n of Tn of b is less than or equal to 2k. All right? And now it's just a simple rescaling argument to show that the sup of the norms are now bounded. So suppose norm of b equals 1. Then the norm of Tn of delta 0 over 2 applied to b is less than or equal to, so for all n, certainly less than or equal to the sup over n of all of these, which is less than or equal to 2k, because this is an element with norm delta 0 over 2, which is less than delta 0. So this is less than or equal to 2k, which implies, so again, Tn is linear, so I should have reversed this. Let n be a natural number. Let b equal to 1. Then, okay. So then Tn applied to b is less than or equal to 4k over delta 0. Now this holds for all b with length equal to 1. And therefore, the operator norm, which is the sup over all b with norm equal to 1, is less than or equal to 4k over delta 0. This holds for all n, and therefore the sup over n of the operator norm is less than or equal to 4k over delta 0, and therefore giving us the uniform bound. Okay? I have time for this. Okay, I don't think I have time for the entire proof of what's to come. So I think we'll just stop there for now.